All right, now let's look at exercise 8.2, which is our second example from our chapter 8 problem set. So this is a CSTR problem, and I will note that there is more details on CSTRs earlier in the chapter with a couple of examples, but let's go. So reactants A and B can react irreversibly to produce either a desired product D or an undesired product U, as shown in the equations below. The corresponding rate expressions are given by this. And so that's my concentration of A and B. R is my molar gas constant, and T is my temperature in absolute units. A liquid feed mixture containing 10 moles A per gallon and 12 moles B per gallon at 350 Kelvin is fed to 25-gallon isothermal CSTR operating at 350 Kelvin at a rate of 12.5 gallons per minute. What is the conversion of the limiting reagent? What is the outlet selectivity in moles D per mole U? The limiting reagent will be the reactant that will be consumed first. Here, for each mole of A consumed, a mole of B is consumed. The limiting reagent will therefore be the species with the smallest concentration of the feed, right? So that's A. Why would the conversion with respect to the limiting reagent be preferred? Well, I can consume all my A in theory, but I can't consume all my B, right? Because once I consume up all my A, there's going to be no more A to react with B. So if I'm looking for 100% conversion, right, I'm going to look at conversion with respect to my limiting reagent because it can go to 100, right, but that of B cannot. For this set of reactions, the following general systems of mole balance design equations will apply. So here I have my mole balance design equation for my CSTR for each species, A, B, C, D, and U. So within this, okay, so again, there's material earlier on CSTRs. Tau is my space-time or mean residence time, so the mean time that a fluid element remains in my reactor. So it's going to have units of time, and so this is going to be equal to the volume of my reactor divided by that inlet volumetric flow rate. Okay, and so volume divided by volumetric flow rate is going to have units of time. Okay, and so if I use volume in gallons, rate in gallons per minute. Okay, tau will have units of inverse minutes, right? Or we'll have units of minutes. Within my rate expression, my pre-exponential term has units of inverse minutes, so that'll cancel out and everything will be okay. Okay, so units are going to be great. Concentrations, what's going to be key is I'm just going to be consistent. So as long as these are all in gallons per minute, right, this CA here will be gallons per minute, right, and all will be good. Or not gallons per minute, moles per gallon. Cool. So these will be in moles per gallon. And so my result that'll be in moles per gallon and everything will be good. All right. So the other comment then is I also have these terms nu in here, right? Nu corresponds to my stoichiometric coefficient. And so I'm looking at the constant in front of each of my terms in my rate expressions. And then just remember for reactants, right, my stoichiometric coefficients could be negative, it's being consumed, and for product it will be positive. Okay, so cool. I'm going to jump over to MATLAB, and I'm going to solve this using fsolve. Okay, and if I'm solving this using fsolve, okay, so there's flash solve our last one. I'm going to create a new script, and I'm going to start out by, well, if I'm going to solve a system of equations using fsolve, the first thing I need to do is I need to write an error function. Okay, so I'm just going to go, I'm going to write res, and so I'm going to call this error, maybe CSTR. It's going to have an input of x. Okay, so key is when I write an error function, okay, for use with fsolve, just like with f0, MATLAB's looking for a function with a single input and a single output. Great. Here I just called my input x. My output is res. What's often confusing to students is my input, right? I just have one variable, but there's actually 8 quantities I'm trying to solve for, or 4 quantities I'm trying to solve for in this problem, right? The exit concentration of all 4 species. And so just remember, right, a variable is just a container, right? It's a container for information. And so x is just going to be a container which will contain those 4 variables I'm trying to solve for. All right, and I should say, right, if I go back to my equations, right, in terms of looking at things, okay, tau, right, tau I know, right, so we said that's volume divided by volumetric flow rate. I have that. Stoichiometric coefficients, right, I have that, right, because I have my expressions. R1 and R2. When I look at R1 and R2, the only quantities in there that I don't know is Ca and Cb. So these correspond to the concentrations of my exit stream. So the superscript naught, that's my inlet stream. Okay. Without the superscript naught, that's looking at my exit stream. So this is dependent on the concentration of my exit stream, which I don't know. So in R1 and R2, right, I just have Ca and Cb that I don't know. Okay, R and T I know. And so when I look at my system of equations, okay, my unknowns are going to be my exit concentration, Ca, Cb, Cd, and Cu as they appear on the right-hand side of my equations, and then Ca and Cb as they appear in R1 and R2. In terms of my inlet concentrations, I know those. We're told that Ca naught 10 moles per gallon, B is 12 moles per gallon, and then D and U, there's no product flowing into our tank initially, so they're just going to be 0. Okay, T is 350 Kelvin, then R, okay, this is joules per mole, T's in Kelvin, only R I remember is 8.314 joules per mole. Okay. All right, so with that said, okay, I come back over to my air function. Okay, and remember the first thing I always do is I unpack. Okay, what I mean by this is, right, is X is just a container, right? X contains these 4 variables I'm trying to solve for. And so I could just reference to, say, X1, X2, X3, and X4. Okay, but I often mess things up when I try and point to specific elements within my equations. And then also that order is going to be the same as the order of my initial guesses. And it's also going to be the order of that vector that I get when fsolve solves my system of equations. And so I want to just make sure I keep track of everything correctly. Unpacking 2 also allows me to assign names to those variables as they appear in my system of equations, so that my expressions, when I write them out, look more like, or make more sense to me, right? And then become easier to troubleshoot and debug. And what I mean by that is I'm going to create some new variable Ca, and Ca is just going to be defined as the first element of X1. Okay. Cb will be the second element. Cc will be the third. And Cd will be the fourth. Okay. The next thing I'm going to do, let me make this full screen, is I'm going to define my parameters. Okay. And what do I mean by that? What parameters do I have? Okay. Well, I'll be able to compute tau. So in terms of tau, so I'll have V was 25, right? Did I get that right? Yeah, V is 25. So that's my volume in gallons. V flow is equal to 12.5. So that's my volumetric flow rate in gallons per minute. So then tau is going to be equal to V divided by V flow. So this is my mean residence time in minutes. Cool. Within my rate, so that's tau. Oh, let me get we'll get my stoichiometric coefficients. So let me get my stoichiometry. Okay, and technically that's new, but I'll just write it as like UA1. So stoichiometric coefficient of A in reaction 1 is going to be -1. Stoichiometric coefficient of B in reaction 1 will be -1. And stoichiometric coefficient of my desired component in reaction 1 will be +1. Okay. Now when I look at reaction 1, U is not present, so it has a stoichiometric coefficient of 0. Okay, and I could just go ahead and I could simplify my mole balance design equations and say kill out this term. But I'm going to keep everything, right? I'm going to keep everything just so that I can write all those equations down, right? They'll be exactly the same, so I can copy and paste like I like to do. But then it'll also give me some flexibility if I wanted to play around and change any of the values, that I could do that and look at the effect. Okay, and so I'm going to say UU1, right, is equal to 0. In terms of reaction 2, UA in reaction 2 is -1. B in reaction 2 is going to be -1. My desired component in reaction 2 has a stoichiometric coefficient of 0. Then my undesired in reaction 2 is going to be 1. Okay, so I have my stoichiometry. And next I'm going to get my inlet concentrations. And those are going to be, boy, I'm having a hard time tonight, gallons, moles per gallon. Okay, and so Ca naught we said was 10, Cb naught was 12, and then there was no D going in initially, so it's just 0, and Cu naught is also 0. All right, and this is, again, I could just come over here, right, and I could kill D naught and U naught and not even write them down. I'm going to include them just so that I can write down all my equations so they look exactly the same. Will help me identify any potential issues or typos, but then also give me the ability to generalize my code later on if I so choose. Okay. So now I'm going to write out my system of air functions. Okay. So I'm going to write to the first, second, third, and fourth element of my output variable. Now when I do that, okay, remember with fsolve, just like f0, I need to take my air functions and I need to write them so that they are they evaluate to 0 when I find my solution. And so for my system of equations, what I'm going to do is just take the right hand side and bring it over to the left. And so for equation 1, it'll look like I'm going to have, I call it tau, times UA1 times, oh, I didn't define my rates. So, okay, hold on. So let me add my rates because I'm going to get more on there. So I was just about to do new A1 times R1, but I said, oh, I don't have R1. So, and before I do that, let me do my temperature. Okay, so my temperature was equal to 350. Bam. And then my molar gas constant. Okay, I want that in SI units. 8.314. Since the numerator is in joules per mole, this is in Kelvin. I want R in joules per mole K. All right, so now when I do that, now we can get my rate expressions. Okay, I'm going to write out my rate expressions just so that my air functions become easier to write. And so R1 of my pre-exponential term, I'm not going to write the units or anything. My units will check out with all the values I'm given. Okay, if it were a real problem, you might need to check. So this is 1.12. Okay, e to the 2. Right, 1.12 times 10 to the 2 times the exponential. It's the exponential of negative 15,300 divided by RT. Negative 15,300 divided by, in parentheses, R times T. R2, R times T times CA, bam. Okay, R2 is 1.87 e to the 2 times my exponential of negative 23,700 divided by R times T times CB. Phew. Okay, so now when I go to my system of air functions, so we have tau times UA1 times R1 plus UA2 times R2 minus CA plus CA naught. So it'll be minus CA plus CA naught all right, when I bring them all over. Okay, cool. Okay, and then what I'm going to do, since I'm not killing terms, is I'm going to copy this, right? And my second element, res2, I'm just going to change A to B. And there's my mole balance for B. Okay. For my third one, I'm changing A to D. So the order of my air functions doesn't matter. Okay. Whereas I said the order of the variables that I'm trying to solve for here matters, and that's going to be the same as my initial guesses. Hey, and look, I just noticed I made a mistake. I was calling this CC up here, right? So we're going to make the third element CD, and then the fourth element CU, right? I was just thinking ABCD, ABDU, right? Now we got this. All right, so now that works. And let me get my undesired, U, 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 and U. Okay. Scrolling up, right? None of these are underlined, right? They're all used. All my quantities that I define up above are used. Okay, and by not killing any terms, my air functions, right, all look exactly the same, right, which is nice in terms of checking, right, to make sure that they're correct. Okay, and actually I'm not going to save it quite yet, because what I'm going to do now is I'm going to add a top function to just automate solving. Okay, I'm going to call this function res is, I'm going to call it, say, CSTR solve with no inputs. Okay, and what I'm going to do is let's start, well, don't even necessarily, well, let me just separate out. So let me just to separate it out in terms of my initial guess. Okay, so I have A, B, D, and U. So A, we start out with 10 moles per gallon. If all the A is consumed, it goes to 0. So it's going to be between 0 and 10. In terms of B, well, B, I'm starting out with 12. If I consume all the A, it can go down to 2. So it could be between 12 and 2. D and U, right? If all the A is consumed, right, could in theory be between 0 and 10. So A, B, D, and U are going to be between 0 and 10. B is going to be between 2 and 12. So what I'm going to do is I'm just going to use a random number generator, and I'm going to just randomly generate concentrations between, for my 4 elements. So rand is between 0 and 1. I'm going to multiply by 10. And so that's going to be a vector of random numbers. So of length 4 between 0 and 10. And so then solving, and I'll use that as my initial guesses. So res is going to be equal to fsolve, and then it'll be at air CSTR, and then I will give it my initial guess, IG. Okay. So now I'll solve this CSTR solve, and this is what I said I want on an exam, is say a script, or in this case it's a function with no inputs, just something that I can just run, right? So I could even have a script in which I demonstrate how to run this, but on my running would be, say, SOL is equal to CSTR solve, okay, no inputs, and if I do it, right, it solves. So here's the concentration of A, right? This is why I like this order. Here's the concentration of B, right? It's 2 moles higher, right? That makes sense. Here's my desired, and here's my undesired. So concentration of my desired and concentration of my undesired species. Okay, cool. All right, so that seems reasonable. Okay, and so what I'm going to do next, though, is the problem action. If I can flip correctly. Okay, so I solve for my exit concentration, so now I know my exit and exit. But it asks for, 2 other quantities. It asks what's the conversion of the limiting reagent. So what do I mean by the conversion of the limiting reagent? So let me call this just SOL. Okay, the conversion of my limiting reagent is how much of my A, or what percentage of my A going in has been consumed. So if 10 moles per gallon of A are going in, okay, and I can calculate the moles of A coming out, I can determine what percentage of my A, right, has been consumed. And I'm doing that for A, right, because there's 10 moles of A, 12 moles of B. I have a one-to-one reaction, so it's possible to consume all of my A, but it wouldn't be possible to consume all of my B, because once all my A is consumed, I'll still have, say, 2 moles of B left, and then that B won't react because there's no A to react with. So what can I do? So in terms of my solution vector, I could just point to the first element. I know that's going to be A, or if I want, I could pull it out, right? So CA is going to be the first element of my solution vector. Okay, and then in terms of, hey, now we're getting crazy, right? So CA naught, I could define it, okay, and we're going to do this a couple different ways. CA naught, here is 10, okay, so CA naught is 10. So in terms of res, let me just say res initially. This is my conversion of A. Okay, my conversion is going to be what went in relative to what came out divided by what went in. Okay, so now if I run it, okay, worked before, I get a conversion of 0.5699. So about 57% of my A has been consumed. It also asks, what is the selectivity, right? So that's basically, I'm just looking for the moles of my desired component relative to the moles of my undesired component, right? Because I want to make it more, what I want to make is D, I don't want U, right? So I want the ratio of D relative to U, so I can get a sense for how much D I'm making relative to U. And so I could kind of pull that out as well. All right, so CD, okay, that's my third element of my solution vector. CU, that's my fourth element. If I can write it correctly. Okay, so now my selectivity. So let's see, do I want to make two optionals? No, let's do it, right? So let's just pack it up in a vector. So I'm just going to res is equal to, and I'm just going to use, so I'm just going to define it. So it's going to be a vector of length 2. There's my first element, and then my selectivity. Oh, so that'll be res 1. Okay, then this will be res 2. It's going to be CD divided by CU. Okay, let me save that. And now if I run this, okay, now I have my conversion, and there's my selectivity. Good. All right, now what I'm going to do just for practice. So here, this would be a valid solution, right? So this would be a valid solution, and that's good. I would just add some documentation to explain exactly what I'm returning. If you wanted to return all the concentrations, you could, right? Because we have them. The one thing I want to do is, well, up here I'm defining this parameter CA naught. It's also being defined here within my air function. It'd be nice if I only defined it in one place so that I'm consistent. Okay, what do I mean by that? So if I ever was told that, oh, the initial concentration isn't 10, it's 5. Well, it'd be nice just to have to look in one place to update it to make sure that it's correctly updated everywhere it needs to be. And so if I need it up here, okay, if the information is needed up here, okay, what would be nice is if I didn't have it here, okay, but I instead passed it as an input variable to my air function. Okay. Cool. So instead of defining it here, I'm going to pass that information to it. Okay. Now I can do that, all right, but now I'm going to have an issue with my fsolve command. Remember, fsolve is just looking for a function with a single input and a single output. Okay. So what am I going to have to do? Okay. Well, I'm not going to define this here. Okay. What I'm going to do is I'm going to just make a comment, my initial concentration of A in moles per gallon. Okay. And then what I'm going to have to do is to get that to my error function, I do that via an anonymous function. So I'm going to call, say, error CSTR reduced is equal to, I want my final error function just to have a single input, say x. When I pass x to this anonymous function, what do I want to do? I want to call error CSTR and pass that value of x to it, along with this value of CA naught here. Okay, and then here, instead of error CSTR, this could be this new error CSTR reduced, and I can get rid of the at symbol since it's now of type anonymous function. So if I run this, I get the same exact answer. Okay, and now in this version, CA naught's defined up here. Okay, and it's not defined within my error function. Instead, I define it in my top function and pass it to it. So now if the problem were to change, with initial concentration of A is 5 gallons per minute, okay, I just need to update it here. All right. What I don't want is to create a logical issue where I say change this to 5, but then forget that it's also defined down here within my error function. All right, and so it's desirable just to have one variable that I need to update for the entirety of that code. So there's problem 8. I said I'm going to come back and I'm going to do a bonus solve as well, where we look at varying tau, but I'm going to keep this as is for my homework solution. Let me know if you have any questions.